this is very nice, because when I apply the Laplace transform to an ordinary differential equation, I am going to get a polynomial. Correct? I am going to get a polynomial. But the advantage is that the initial conditions are taken into account. This makes it particularly conducive for solving initial value problems. When you want to solve initial value problems, the Laplace transform is very useful, because it takes into account the initial conditions. Just brief summary, L of f prime equal to S f of s minus f of 0. There is the derivative has become multiplication by s. L of t f is minus f prime, multiplication by t has converted to differentiation. Second derivative, you see a multiplication by s squared, multiplication by t squared goes over into second derivative. Third derivative has become multiplication by s cube, multiplication by t cube has become third derivative. So let us now take a simple example. You can just write down the equations. Y double prime minus plus 3y prime plus 2y equal to e to the power minus t, correct. Y of 0 is 0 and y prime 0 is 0. Y of 0 is 0, y of 0 is 0 and y prime of 0 is also 0, correct. So now let us denote the Laplace transform of little y by capital Y, correct, and you take the Laplace transform of the differential equation. Look at the table is right on top of you. Laplace transform of y double prime will be s squared Laplace transform of y minus sy0 minus y prime 0 plus 3 times Laplace transform of y prime, which is s times Laplace of y minus y of 0 plus 2 capital Y, because Laplace transform of little y is capital Y. Right hand side, what do you have? E to the power minus t. What is the Laplace transform of e to the power minus t? 1 over s plus 1. And left hand side has simply become algebraic equation, linear algebraic equation with a polynomial coefficient. So what do you get? The initial conditions are 0. So all the terms involving y of 0 and y prime 0 disappear, and you simply get s squared plus 3s plus 2 capital Y equal to 1 over s plus 1, or capital Y equal to 1 over s plus 1 the whole squared plus into s plus 2. So now I have to recover the little y from the capital Y, right. Capital Y is known, the Laplace transform of the solution is available. Now you need to recover the solution little y. So what do? You write down the partial fraction decomposition for 1 over s plus 1 squared into s plus 2. A by s plus 1 plus b by s plus 1 squared plus c by s plus 2. Go through the same procedure for finding a, b and c. If you do the algebra correctly, the a will turn out to be minus 1, the b will turn out to be 1 and the c will turn out to be 1, and so your capital Y is exactly 1 over s plus 1 squared minus 1 over s plus 1 plus 1 over s plus 2. So what is the function whose Laplace transform is s plus 1 squared? T e raised to the power minus t. So this is nothing but Laplace of t e raised to the power minus t minus e to the power t plus e to the power minus 2t. So now use the uniqueness theorem, right. Capital Y is what? Laplace of little y. Laplace of little y is Laplace of this business. So little y must be this business over here, correct. So you use the uniqueness theorem. So solution is exactly t e to the power minus t minus e to the power t plus e to the power minus 2t. Now let us take stock of the situation. What would you have done if you did not use Laplace transform but directly do it by other conventional methods? What are the other methods? Method of variation of parameters and method of undetermined coefficients. So, if you want to apply the method of undetermined coefficients, what would you do? First find the complementary function, first find the complementary function, right, and then find the annihilator for the right hand side and find the particular integral, and then y will be equal to complementary function plus particular integral, and then after doing all this you have to now use the initial conditions and you will get a system of equations for C1 and C2 which has to be again solved. This problem was not there when you apply Laplace transform, because right in the first step the initial conditions have been incorporated into the system. There is no question of finding the complementary function separately and the particular integral separately. There is no question of finding annihilators. There is no question of trying to remember whether the right hand side, the annihilating polynomial has roots in common with the characteristic polynomial or not. Nothing is required. And at the end of the day, you do not have to go back and solve a system of linear equations for finding the constants. It is already built into the system. The Laplace transform method is superior to the method of undetermined coefficients and the method of variation of parameters. Of course, the method of variation of parameter wins when the right hand side is not of exponential type. Suppose the right hand side is e to the power t squared, I can't even apply the Laplace transform. And of course, the method of variation of parameter works for variable coefficient equations. So, method of variation of parameters is a different, has different merits, but as far as method of undetermined coefficients is concerned, the Laplace transform is far superior. Okay. Another advantage of the Laplace transform is that it does not have to be a single equation, you can even do it for a system of equations. I take y1 prime plus y2 equal to 2 cosine t, y1 plus y2 prime equal to 0. Just write the equations, do not write anything else, work out the algebra yourself. Just write this, this and this, nothing, the detailed algebra can be written out later, correct. So, taking the Laplace transform of these two equations, what do you get? You get a pair of linear equations for capital Y1 and capital Y2. When you solve for capital Y1 and capital Y2, you get rational functions of S, and then partial fractions and other things, and you recover your little y1 and little y2. Again, initial conditions have been incorporated into the solution procedure and there is no need to determine them separately. It can even be of second order, there is no reason why the differential equation should be of the first order. You can have pairs of equation of second order, you can have a single equation of second order, correct. You can have pairs of second order. So, write down these problems, there is a page of problems for you for your amusement, right. For a long time you have been, I had deprived you of this amusement, now here it is. Just write the equations, and be quick about it. The last one is very interesting if you notice. Show that a particular integral of d dx plus a to the power ny equal to x to the power m e to the power minus ax is gamma m plus 1 upon gamma m plus n plus 1 into x to the power m plus 1 e to the power minus ax. This is very interesting, the last one is particularly interesting. Try to get it from Laplace transforms. Here you want a particular integral for the last one, correct. So, solve the differential equation completely with initial conditions 0, 0, 0, 0, 0. Take y of 0 equal to 0, y prime 0 equal to 0, y double prime equal to 0, y n minus 1 equal to 0. Assign all the initial conditions to be 0 and find the solution. After all, you only want a particular solution, no? You are only asking for a particular solution, and when I apply formulas of Laplace transform, the initial conditions will be floating around. take them all to be 0, correct. So, hint, take, solve using Laplace transforms with 0 initial conditions. Solve using Laplace transforms with 0 initial conditions. Pretty routine questions, there is nothing fancy about this, and this is the sort of questions that will be given to your students. But make sure to tell them the merits of the Laplace transform method for the last one, because you only want a particular solution. No? See, I want to simplify my life. When I apply Laplace transform, y0, y prime 0 and all will float around, and once I declare them to be 0, the expression will become very simple and I will get the solution. I only want a particular solution, I do not want a general solution. Right. Done? Yeah. Next, you see, in the Laplace transform method, we took a system of equations, y1 prime plus y2 equal to something, y1 plus y2 prime equal to something. We took a system of first order ODEs, right. We took a system of first order ODEs. There is no need to take a system of first order ODEs. I could take two equations simultaneously, which are both of the second order. I could solve x double prime plus y equal to sin t, x plus y double prime equal to cos t. I can apply Laplace transform directly. Okay, here are some exercises of that kind. X double prime minus x plus y prime minus y equal to 1, y double prime plus y plus x prime minus x equal to 0. X of 0 is 1, x prime of 0 is 0, y of 0 equal to 0, y prime of 0 equal to 1. Look at this. Directly apply the Laplace transform, finished. There is no, see, the procedure can be described in a nutshell without having to distinguish cases. That is a beauty of this Laplace transform method. Conventional methods are not as efficient as Laplace transform methods for solving constant coefficient equations. For example, take this one, y double prime plus y2 equal to minus 5 cosine t, y2 double prime plus y1 equal to 5 cosine 2t. What is the other procedure for solving systems? What other procedure is there? Take a system of first order ODEs. If you recall, what is the other procedure? There is a procedure, but we should understand the merits and demerits of that also. And the last couple of them are on shifting theorems. We also discussed shift theorem, right? The first shift theorem and the second shift theorem, and we looked at two simple examples. Here are two more for you. Here are two more examples on shift theorems, or finding the inverse Laplace transform. The Laplace transform is given to you, you have to recover the original function. The last one is an example in the Laguerre polynomial, the Laguerre equation, remember? Laguerre equation. This problem is from Kaplan's book. Kaplan's book on ODEs. Kaplan's book is not available, it is out of print. It is a good book, there are several good books on ODEs. If you find some good examples, just use them for illustrating. This is from Kaplan's book. Alright, shall we proceed? No? Why? You are slowing down. So, okay, so now those of you who have finished writing, please recall what is the other conventional method for solving systems of differential equation. How does a system of differential equation look like? Linear, constant coefficient, nothing fancy. Yeah, dy by dt, yeah, dy by dt equal to ay plus b, right? How does it look? Y prime, y is a vector, like y1, y2, y1 prime equal to a11, y1 plus a12, y2 plus a13, y3, correct? y2 prime equal to a21, y1 plus a22, y2 plus a23, y3, etc. You will write it as a system, right? Y prime equal to ay, where a is a matrix. That will be the homogeneous constant coefficient first order system. And then there could be a forcing function, right? It will be y prime equal to ay plus b of t or r of t, whatever. Now, how will you solve the system? How will you solve the system of equations? No, you try to look for eigenvalues and eigenvectors for A. That is the procedure for doing it, but unfortunately this procedure has a disadvantage. When A is a non-diagonalizable matrix, you will be in serious trouble. If the matrix has a basis of eigenvectors, this procedure will also work, and you can write down the solutions. If the matrix does not have a basis of eigenvectors, if it is not diagonalizable, then you are going to be in trouble. The solution procedure becomes much more complicated. This is for the homogeneous ODEs first, for finding the complementary function. Then you have to solve the inhomogeneous ODE, and then you will have to add the complementary function plus particular integral. Even if it has a basis of eigenvectors, suppose, even if it has a basis of eigenvectors, you have to find the eigenvalues, you have to find the eigenvectors, and you have to find the write down the complementary function, and then you have to find the particular integral, and then you have to write the total solution, and then plug in the initial conditions and get a system of linear equations for the constants, right? This is the solution procedure. But then the Laplace transform short circuits all these things. It does not even care whether the matrix is diagonalizable or not. It straight away proceeds and gives you the solution. It does not care whether it is a first order ODE or a second order ODE. It straight away goes ahead and produces a solution. So, you see how superior the Laplace transform is. Using linear algebra, using eigenvalues and eigenvectors is far inferior to the Laplace transform procedure. Laplace transform procedure wins overwhelmingly when it comes to systems. All right. So, it is an exceedingly important procedure, it is an exceedingly important solution method for solving ODEs. It is used extensively in areas like control theory and electrical engineering and stuff like that. Laplace transforms are very frequently used, and they are very, it's one of the most important techniques we should know, and you should emphasize this when you teach these courses. You should point out the merits and demerits of the various solution procedures. You have seen several ways of solving it. If you have a constant coefficient system, now you have 3 different ways of doing it: method of undetermined coefficients, method of variation of parameters, and method of Laplace transforms. You must point out the merits and demerits of each procedure. You must understand them, and you must point this out to your students. Okay. Now, in all those examples that are given you, s cube upon s to the power 4 plus a to the power 4, s squared minus a squared upon s squared plus a squared the whole squared. All those examples, the rational function that we took was very special. it is what we would call as a proper fraction, right. The degree of the numerator is less than the degree of the denominator. Look at all the other examples. Laplace transform of cosine t is s upon s squared plus 1. Laplace transform of sine t is 1 over s squared plus 1. So, what do you know about the Laplace transform? Laplace transform of 1 is 1 over s, and Laplace transform of e to the power t is 1 over s minus 1. What do you notice about all these things? They all go to 0 as s tends to infinity. The Laplace transform goes to 0 as s tends to infinity. It goes to 0 at a variety of in variety of ways. Laplace transform of sine t is what? 1 over s squared plus 1. It goes to 0 faster than the Laplace transform of cosine t. Laplace transform of cosine t is s upon s squared plus 1. It goes to infinity slower. Why? What is so special about sine t? Why is it that the Laplace transform of sine t decays to 0 faster than the Laplace transform of cosine t? It's not fair, isn't it? After all, sine and cosines are both so similar, the graphs are just getting shifted by a little bit, that's it. After all, the functions are going hand in glove, no? Sine and cosine, and yet why is it that the Laplace transform favors sine is than the cosine? Have you ever thought about this? This question has never occurred to you, right? But isn't it an interesting question? And I think one should understand this a little better, isn't it? It's well worth thinking about this. First of all, I don't know whether you recognize the fact that the Laplace transforms of all the functions that you computed, they all go to 0. So if I ask you, find me a function whose Laplace transform is 1, it's unlikely that such a function exists. Looking at all these examples should tell us that there must be something going on here. There must be some interesting theory that underlines this, right? We should be able to prove a theorem that if f is of exponential type, then the Laplace transform f of s tends to 0 as s goes to infinity. That should be a theorem. That's supposed to be a theorem. And then when I ask you, give me a function whose Laplace transform is 1, you will say such a function doesn't exist, because as per the theorem, the Laplace transform of a function of exponential type should go to 0, correct? So now you see that it's important to know some little bit more about the behavior of the Laplace transform. And this other question is very interesting. Why is it the Laplace transform of sine t is better behaved than the Laplace transform of cosine t? Yes? No, let us not stray away from this question. This question that we are now focusing our attention on is, why is it that the Laplace transform of sine t goes to infinity like 1 over s squared, and the Laplace transform of cosine t is going to infinity at the rate of 1 over s? Remember the shifting theorem. What did we, there was a very simple and innocent observation that we made, which is the same as, what is it? Laplace transform of f is the same as Laplace transform of f into h, where h is the Heaviside function, correct? In other words, what are you doing? You are taking the function f and you are essentially ignoring what is happening for t less than 0. For t less than 0, it is defined to be 0, correct? In other words, you are taking the graph of the function and you are replacing the left hand on the left half plane. The graph is just replaced by the line. So you are looking at f of t for t less than 0 is redefined to be 0. When you do this with a cosine function, what do you get? F of t equal to cos t when t is bigger than 0, 0 when t is less than 0. Now what happens to the graph? It has a jump discontinuity at the origin. When you do it to the sine function, what happens? There is no jump discontinuity. So when you multiply the function by the Heaviside function, the resulting function is continuous at the origin when the function f of t is sine t, and it is discontinuous at the origin when it is a cosine. That is, when you clip the graph and make it 0 on the left, then the cosine function suffers a jump discontinuity, but the sine function does not have a jump discontinuity. And so the sine function is nice at the origin. It has one-sided derivatives also. Not only is a sine function after making it 0 for negative values, not only is it continuous, it is much more than that. It has a right hand derivative and it has also a left hand derivative. The derivative suffers a jump discontinuity, but the function is continuous and the one-sided derivatives exist. That is also, do not forget that. That is also an important point. So it is really nice. And so this is reflected by the faster decay of the Laplace transform. So that is the reason why the sine function, the Laplace transform of the sine function decays faster. So when the functions have bad behavior at points, these bad behavior is reflected in the decay properties of the Laplace transform. So there must be a very close relationship between the decay properties of the Laplace transform and the regularity properties of the function. Is it continuous? Does it have a jump discontinuity? If you take 1 over root t, it is much worse. What is the Laplace transform of 1 over root t? Root pi by root s. And the Laplace transform is decaying like 1 over root s. It is worse than the cosine function. For the cosine function, the Laplace transform goes to infinity like 1 over s. Whereas for 1 over root s, the Laplace transform is going to infinity like 1 over root s. 1 over root t, Laplace transform goes to infinity as 1 over root s. So still slower. Why is it? Because 1 over root t is not only discontinuous after multiplication, after clipping the graph, not only is 1 over root t going to be discontinuous, it is not just a jump discontinuity, it is an infinite discontinuity. It is a much worse type of discontinuity. And this is seen by the slower decay rate of the Laplace transform. This relationship between the decay properties of the Laplace transform or the local regularity of the function is extremely important in analysis. The same phenomenon you will see in Fourier series, the same phenomenon you will see in Fourier transforms. Take the Fourier series of the square wave, take the square wave train, f of x equal to 1 between 0 and pi, equal to minus 1 between pi and 2 pi, equal to 1 between 2 pi and 3 pi, 1 minus 1, 1 minus 1, 1 minus 1, square wave train. Compute the Fourier coefficients of the square wave train and see how fast do the Fourier coefficients decay. Take the sawtooth wave, take the triangular wave like this, where the graph is continuous. It will decay faster. So the better the function, the faster will be the decay of the Fourier coefficients. Same thing you will see in Fourier transforms. So this relationship between the local smoothness and the decay in the Fourier transform or the Laplace transform or the Fourier coefficients is extremely important and a recurrent theme in modern PDEs. If you want to understand PDEs deeply, you must understand this relationship very closely. Correct. Unfortunately, we won't be able to do any justice to this in this course. We will only prove one theorem, and the theorem that we are going to prove is called the Riemann-Lebesgue lemma. The Riemann-Lebesgue lemma says that if f is of exponential type, the Laplace transform of f goes to 0 as s tends to infinity. Proof is very simple. Do not write down the proof. There is no need for you to write down the proof. Just write the statement of the Riemann-Lebesgue lemma. It is called a Riemann-Lebesgue lemma. Very strange, right? You will always call the mean value theorem. There is only one Lagrange's mean value theorem. Correct? There is only one Cauchy integral formula in complex analysis. But here I am calling it a Riemann-Lebesgue lemma because there is a Riemann-Lebesgue lemma for Fourier series and there is the Riemann-Lebesgue lemma for Fourier transforms also. And so we have a class of theorems, all of which assert that something goes to infinity if something is nice. The Fourier coefficients go to 0. For a 2 pi periodic function, the Fourier coefficients go to 0, the Fourier transform goes to 0, the Laplace transform, they are all called Riemann-Lebesgue lemmas. The class of theorems, there is a Riemann-Lebesgue lemma for Fourier transforms, there is a Riemann-Lebesgue lemma for Fourier series, they are all of the same type. For the Fourier series, it asserts that the Fourier coefficients goes to 0. For the Fourier transform, it asserts that the Fourier transform goes to 0 and so on. How do you prove such a theorem? First of all, you have to apply the definition of exponential type. You get an inequality. And then the 0 to t naught is a proper Riemann integral or an improper integral. But if it is an improper integral, it is converging absolutely. Correct? So now what we will do is the following. Let us take an epsilon greater than 0. As always, we have to show something goes to 0. So let us take an epsilon greater than 0 and we have to produce an s such that Laplace of f at s is less than epsilon when s is bigger than or equal to s naught. That is the usual thing. First look at this integral from 0 to delta. By the Cauchy's principle of convergence, there is a delta such that this contribution is going to be less than epsilon by 3. Because this integral is a proper Riemann integral or a converging improper integral. If the function is continuous in a neighborhood of origin, then this is absolutely trivial. If the function is, if it's an improper integral at the origin, then this follows from the Cauchy's principle of convergence. In either way, there is something of this kind. So the 0 to delta is one piece. Then you do the following, you take m to be the integral from 0 to t naught mod ft dt. Take m to be the integral 0 to t naught mod ft dt. Let us look at the contribution from delta to t naught. E to the power minus st can be written is less than or equal to e to the power minus delta s. This function, this piece, this factor e to the power minus st is less than or equal to e to the power minus delta s, and so I pulled it out of the integral and I am left with this, and this is less than or equal to m, and as s tends to infinity, I have this particular business over here e to the power minus delta s, which will go to 0. When what is the remaining piece? T naught to infinity. From t naught to infinity, use the fact that f is of exponential type, so it is less than or equal to a times e to the power omega t. You can actually calculate this integral and you get a times a upon s minus omega, and this goes to 0 as s goes to infinity. So the integral has been broken into 3 pieces: 0 to delta, where the contribution is less than epsilon by 3. The second piece gives me this, which will be less than epsilon by 3 for all s large enough, and the third piece gave me this, which will be less than epsilon by 3 for all s large enough. So the 3 epsilon by 3's will add up to give me an epsilon. That's it. Khatam. So the Laplace transform goes to 0 as s goes to infinity. That's one of the Riemann-Lebesgue lemmas. Correct? Really clear? So, let us look at one simple instance of this, and then let us go for t. All right. Find the Laplace transform of sin t by t. Find the Laplace transform of sin t by t. So, let us put f of t as sin t by t. What is the Laplace transform of t times f of t? Laplace of sin t, which is 1 over 1 plus s squared. But on the other hand, what is the Laplace of t f of t? Minus f prime of s, correct? So, I have the equation minus f prime of s equal to 1 over 1 plus s squared. So, f of s is what? Integrate f of s is c minus tan inverse of s. How do I determine this c? The additive constant of integration. Appeal to the Riemann-Lebesgue lemma, and as s tends to infinity, this should go to 0. So, the only choice for the constant is pi by 2, correct. So, the Laplace transform of sin t by t is cot inverse of s. So, you will need the Riemann-Lebesgue lemma for actually determining constants of integration sometimes, and this is also a typical use of boundary conditions, right. Riemann-Lebesgue lemma is a boundary condition. Use the boundary condition for finding constant, correct. So, according to Riemann-Lebesgue lemma, certain functions like f of s equal to 1 cannot be the Laplace transform of any f t of exponential type. There is a great deal more we could do. I think I will reserve that for tomorrow's class. So, tomorrow we will continue with Laplace transforms. That will be the third session, and we will then prove we will look at lots of examples. We will go further and see some applications to computing improper integrals. We will also look at other techniques for recovering the original function from the Laplace transforms. Then we have to do the convolution theorems. Then we have to do the applications of convolution theorem to differential and integral equations, and we will prove the beta gamma relationship. We will look at the Abel's integral equation. We will look at an application of Abel's integral equations to the Tautochrone property of cycloids and stuff like that. Okay. All right. So, we will stop here today.